Okay, all right, we'll get started. Let me share a screen here to show you some stuff. All right, let me get my list up. Here we go. All right, there we go. Okay, so in the folder for chapter or for unit 5, I added some more things. There's a thing here that says Honors Chemistry Ionic Naming Part 2, and this has materials about naming and writing formulas for polyatomic ion containing compounds, which I'll tell you about in just a minute, and problems about naming and writing formulas for compounds with transition metals. And the ones with transition metals, we'll do those tomorrow. There's also this chart here that says Polyatomic Ion chart. This is an important reference that you need to use. So what this has is ions that are called polyatomic ions. Poly means many, and atomic atoms. So ions that contain 2 or more elements. And this chart shows the names, the formulas, and the charges for all of those ions. You don't have to memorize this chart. It's a chart that you can use. So like, for instance, there's a polyatomic ion called carbonate, and that's CO3 with a charge of 2-, or dichromate, Cr2O7 with a charge of 2-. So the name, the formula, and the charge. And the charge is what you use to help determine like how many of those polyatomic ions are present. At the bottom of the chart too, there's this list, which is not that exciting, but we'll use it tomorrow with naming ionic compounds that contain I just got a notification that my connection's not good. If my sound's not good or if it's all choppy, write that in the chat or something so I know. Wait, he's not even in this class. Oh yeah. Okay, so that chart's there, and then if we just go back, there's this thing that says Polyatomic Ion Compound Practice. And these are example problems that I'll do with you. We'll do half of these together, and then the other half you can do as practice for tomorrow. In other words, like finish it up as practice, and then tomorrow at the beginning of class we'll go over them. So we'll do like the first 6 of these, and then the first 6 of these, and then there's 4 more that you can do for practice. That's what the polyatomic ion compound practice is. So today is all about naming and writing formulas for polyatomic ions. This has notes in it. This is the chart that you can use for reference, and then this is the practice. The transition metal ionic compound practice, that's for tomorrow. I just happen to put it there now. All right, so let me switch to something different. Let's see, do this. Okay, I'm gonna actually put this on a different screen to look at. Yep, I think it stayed. Oh, that didn't work. Huh, okay, I can't change screens. I just learned that. All right, so this thing says naming compounds part 2. There's a little check here in case you want to do another practice with sodium nitride, potassium bromide, aluminum oxide, magnesium sulfide. That was like an extra check that we would have done in class if we were live. Okay, so all the ions that we've already talked about are what we call monatomic ions. The prefix mono means 1, but we don't write monoatomic with M-O-N-O-A-T-O-M-I-C. We leave that O off of mono because it's kind of awkward to say monoatomic, and it's kind of awkward to have an O and an A beside each other. So in chemistry, we just call them monatomic. But you can think of the prefix mono meaning of 1. Monatomic ions are ions from elements that contain only one individual atom. So like, for instance, sodium, when it's an ion, is Na+, chlorine, when it's an ion, is Cl-, and so on and so forth. Polyatomic ions are ions that contain two or more atoms, and it turns out that those atoms are bonded covalently, but the covalent bonds between the shared atoms end up losing or gaining extra electrons in order to fill the Lewis structure. And we'll work later on about how those polyatomic ions are formed whenever we write covalent compounds, and you'll see the relationship between polyatomic ions and similar compounds. For instance, that OH, that's pretty close to water, because all that OH is missing to become water is another hydrogen. So HOH is a formula for water. Or like the NH4 plus, that's the ammonium anion, and that's pretty close to ammonia, which is NH3. So the neutral compound that's an ionic compound, or the neutral covalent compound, is NH3, but NH4 plus happens to be a polyatomic ion. So what it means to be a polyatomic ion is that it's actually a covalent compound that forms an ion, and that ion can bond to other ions. So for instance, on the monoatomic ion list, you've got like sodium, which is Na+, and that sodium and the hydroxide, that's the OH minus, those can bond to form an ionic compound. So there's some particular rules and complications about polyatomic and monatomic ions. On the periodic table, the monatomic ions are highlighted here. There are a few others sometimes, but generally all the ones that we've worked with so far, the monatomic ions, elements from group 1 and group 2 are typically lithium through cesium, magnesium through barium. Beryllium and hydrogen are left off here because hydrogen, it's actually a little complicated. Hydrogen, when it bonds with these elements, actually forms usually covalent compounds that are acids, and beryllium doesn't typically take part in ionic bonding. These are transition metals, which we'll study a little bit tomorrow, and aluminum is the only common ion that forms ionic compounds. And then in the upper right-hand corner in the P block, these are the common anions from carbon, nitrogen, oxygen, or nitrogen, phosphorus, oxygen, sulfur, selenium, tellurium, and then the halogens, fluorine, chlorine, bromine, iodine. The polyatomic ions are formed as these compounds, like I mentioned, and this is from the polyatomic ion chart. And some of them are very common, some of them are a whole lot less common. The most important and most common ones that you'll hear and see are the ammonium, the hydroxide, nitrate, carbonate, and sulfate. And a few things about these polyatomic ions, they don't always end with "ide." So a trick with determining if a compound is ionic or covalent with monoatomic ions is anytime the cation or the anion is monoatomic, it always ends with "ide," like sodium chloride, magnesium fluoride, potassium bromide. Here with polyatomic anions, the names don't always end with "ide." They do in a few cases, but they can end with "ium" or "ate" or "ite." I guess that's about it. And also, they can also end with "ide." So the names don't always end with the same sort of thing. And you'll even see that sometimes there are some that look similar, like the NO2 minus is called nitrite. The NO3 minus is nitrate. And it's very important that those are spelled correctly, because if you're referring to nitrite, that's NO2, but if you refer to nitrate, that's NO3. You can get those confused. Same with chlorite and chlorate, and there's also this perchlorate. So there's ClO2, ClO3, and ClO4, and those have names that look somewhat similar, but they're different. Okay, so how things can be different with polyatomic ions and why there can be different forms of them is, for instance, there's a nitrate anion, which is a nitrogen and 3 oxygens. And the reason why there's a double line between the nitrogen and oxygen is that's a kind of bond called a double bond. And I'll show you how those work whenever we do stuff with covalent compounds. But so that's why it looks a little bit different in the picture. But there's a nitrate anion, which is NO3. There's also a nitrite anion, which is NO2. And the reason why the names are different, and we have a naming scheme, is that ite has fewer electrons than the 8 anion. So whenever we think of ions, if it ends with 8, it has more, and if it's ite, it has fewer. That's one of the tricks, one of the parts of nomenclature. You don't have to memorize that, but that's why there is a bit of a difference. Okay, so here's how the names go. Polyatomic ions always form compounds that end up with 3 or more elements. And in polyatomic ions, there are polyatomic ion compounds. There's always at least one polyatomic ion. And where it says it helps to circle the ions, I'll show you a trick about that with determining names. But for instance, this is a polyatomic ion. It says NaNO3. You can identify that it has 3 or more atoms, 3 or more elements, because we have got this capital N in Na, that's sodium. There's another capital N, that's just nitrogen. And there's a capital O, that's for oxygen. So there's 3 different elements. You identify an element with a capital letter. So 1, 2, 3 capital letters, sodium, nitrogen, and oxygen. But it's not a compound where you name it with sodium, with nitrogen, and with oxygen. Instead, on that polyatomic ion chart, this NO3 is on the chart. Here, let me switch back to that. So you see NO3, that's right here. The NO3 minus, that's nitrate. So the reason why this compound, NaNO3, is called sodium nitrate is that it's formed with the sodium anion, which is right here, that has a charge of 1+, and with the nitrate anion, NO3, which is 1-. So you have a sodium ion with a charge of 1+, and a nitrate anion with a charge of 1-. The name doesn't change from what's listed on the ion chart. So you don't like change the name to ide or something like that. You just leave the name just like is listed on the polyatomic ion chart. Here's K2SO4. So one way to know how the name comes about is because this contains 3 or more atoms, you can think about KSO4 and take a look on here, and you'll find this SO4 is the sulfate anion. So what happens is potassium, which is right here on the periodic table with a charge of 1+, gets together with the sulfate anion and becomes sodium sulfate or potassium sulfate. So you have potassium and the sulfate anion, and the name is just potassium sulfate. The metal stays with its regular name, and the anion name comes from the anion chart. And then here, AlHCO3. So I'm trying to let Porter in. I don't know if his Wi-Fi is not good or something. He might be in now. I keep trying to hit accept. Anyway, so you have aluminum and then this HCO3. And I'll show you about these parentheses with this 3 in just a moment. But the HCO3 is right here. That HCO3, it's called hydrogen carbonate or bicarbonate. Sometimes it's called bicarbonate, sometimes it's called hydrogen carbonate. Typically, it's actually called bicarbonate. And for instance, sodium bicarbonate, when sodium bonds with hydrogen carbonate, it makes sodium bicarbonate. That's what baking soda is. So anyway, we have aluminum, that's the metal, and then hydrogen carbonate or bicarbonate. Aluminum bicarbonate would be an acceptable alternative name. So that's the naming scheme. You'll also see it called these polyatomic ion compounds will be referred to as ternary ionic compounds. So ternary refers to having 3 or more. Like there are different prefixes to mean 1, 2, and 3. 1 sometimes has the prefix un or mono. 2 usually is bi or di. And 3 is oftentimes tri or tert or turn. So for instance, like a 3-wheeled bicycle, well, there's bicycles which have 2 wheels, but a tricycle has 3. But then also sometimes things are called primary, binary, and tertiary, meaning like 1, 2, or 3. Let's see, bad connection. Yeah, Porter, it's cool. I kept trying to hit accept, but it kept like throwing you off too. I'll just keep hitting accept if you keep getting bounced off. Okay, so ternary just refers to the fact that there are 3 or more. Now there's a trick with dealing with binary compounds if you need more than one of the ionic or of the polyatomic ion. So for instance, sodium sulfate. Sodium has if you try to form a compound between sodium and the sulfate anion, whenever you look up on the ion chart, you'll find sodium 1+, and sulfate is SO4 with a charge of 2-. And you can do that cross-down method to determine how many of each you need. If you're going to form a compound between sodium and sulfate, then it's going to have to be neutral. Because sodium has a charge of 1 and sulfate has a charge of 2, you're going to need 2 sodiums for every 1 sulfate. So the formula for the compound has to have 2 sodiums. So 2 sodiums makes it Na2, and then it's SO4. That way there's 2 sodiums for every 1 sulfate. But and this one kind of mixes in a metal. There's an ion, iron 3, which has a charge of 3, and hydroxide. So if you look up hydroxide on the ion chart, you'll find OH. So right here, OH minus is hydroxide. The hydroxide anion has a charge of 1-. You can also just write it just as minus. Because you need 3 hydroxides to go with every 1 iron, we need to show that there has to be 3 hydroxides. And every time you have more than one of a polyatomic ion, you put that polyatomic ion in a parenthesis. So since we need 3 of the hydroxides, the hydroxide goes inside a parenthesis with a 3 outside of it. We don't write it as like Fe and then O3H3. And also, if you don't include the parenthesis, that would only mean that there are just 3 hydrogen atoms and not also 3 oxygen atoms. So this polyatomic ion, OH-, that thing stays the same as an OH ratio of 1:1, but has to go inside a parenthesis. And then whenever you see this formula, it's also a sign that it is an ionic compound. So generally, if you see a ternary compound, meaning a compound with 3 or more atoms, and there's a parenthesis, it's usually always an ionic compound and not a covalent compound. In the example of ammonium carbonate, both ammonium and carbonate are polyatomic ions. On this polyatomic ion chart, there are really only 2 polyatomic cations, ammonium and the hydronium. Everything else on this polyatomic ion chart happens to be an anion. You see they all have charges of minus from hydroxide down the first list, and then on the second list they're all negative. But the ammonium and the hydronium, those both have a charge that's positive. So it's possible you could have an ionic compound made with ammonium, which is polyatomic, along with a monatomic anion. But in this example, there's ammonium and carbonate. The ammonium has a charge of 1, and the carbonate has a charge of -2 or 2-. So in order for that compound to be neutral as an ionic compound, you need 2 ammoniums to go with every 1 carbonate to make the compound neutral. And if you need 2 ammoniums, this whole NH4 goes inside a parenthesis, and then you put the 2 on the outside of it. So the parenthesis, whatever's inside the parenthesis is the polyatomic ion. The 2 on the outside tells you need 2 of them. It's also a clue as to what the charges must have to be. So when I look at this compound, NH4,2CO3, ammonium carbonate, because there had to be 2 ammoniums, that lets me know that the carbonate probably has a charge of 2. And because there's only 1 carbonate, that tells me that the ammonium must have had a charge of 1, because whatever the charge for ammonium is, that's how many carbonates you need. Whatever the charge for the carbonate is, that's how many ammoniums you must need. So let me show you in some examples, because the best way to really learn how this goes is by a practical example. Let me switch to a different thing. Well, first off, let me show you where I'm going to get this from. So you could write this down and you want to complete these problems, but in the folder for chapter 5, there's this document here that says Polyatomic Ionic Compound Practice. And we're going to do some of these right now, and then you can have some to do for practice. So this Polyatomic Ion Compound Practice, that's where I'm getting what I'm about to show you, which is this thing here. Yep, that looks okay. Get my stylus. Okay, so what I have on this screen is I've just got a reference for all the polyatomic ions, and that way, like, I can just see them real quick. And then these are the practice from the top half of the page, and there's a, do it like this. There's the name of the compound, and we need to be able to write what the formula is. So it's not uncommon to see compound names like this: sodium chromate, magnesium nitrate, cesium chlorate. And all the time, whenever you write the formula, you got to find the ions that make them up. So first off, sodium, well, that's just the name of an element. And on the periodic table, sodium is in group 1. And if you have a periodic table handy too, that's good. It just says my internet connection is unstable. All right, so sodium on the periodic table is in group 1, has a charge of positive 1. I'll write it as 1 plus because that's like the actual proper way to do it. And then chromate, well, it might be like, chromate sounds like chromium, except if it were just chromium, there's a couple issues. Chromium is a transition metal in the middle of the periodic table, and if this were a monatomic ion, it would end with "ide," definitely end with "ide." So chromium would change to chromide, but this says chromate. And also, whenever you look on the polyatomic ion chart, you'll find right here is chromate. Chromate is CrO4 with a charge of 2 minus. So the 2 ions that make this compound up are sodium, 1 plus, and chromate, CrO4, 2 minus. And what we got to do is write a formula for that compound so that it's neutral. Well, if sodium has a charge of 1 and chromate has a charge of 2, we're going to need 2 sodiums for every 1 chromium, for every 1 chromate. Or you can do that cross-down method where the number of sodiums becomes the number of chromates and the charge for the chromate becomes the number of sodiums. So we're going to need 2 sodiums, and since sodium is monatomic, we can just write as Na2, and then the CrO4, we only need 1 of them, it's just CrO4. So that's the correct formula for sodium chromate. 2 sodiums because the charge for chromate was 2, 1 chromate because the charge for sodium was just 1. So that's all you got to do for that one. We'll do the first 6 together. I'll leave the other 4 for you to do for practice. So calcium carbonate. On the periodic table, you'll find calcium is in group 2, so it has a charge of 2 plus. And then carbonate, well, carbon, that sounds like, you know, the element carbon, except carbon is in group 14. It would have like 4 valence electrons. If it were to have a charge as an ion, it would be like 4 plus or 4 minus, but that's not really a thing. And if it were a monatomic anion, it would be called like carbonide, which isn't a thing at all. Instead, on this chart, carbonate, and it's in alphabetical order. Carbonate is CO3, 2 minus. So you have CO3, 2 minus. Those are the two ions that make it up. And because each of the ions has a charge of 2 plus and 2 minus, you only need one of each. So just the same as whenever you had a polyatomic or a ionic compound with 2 monatomic ions with a charge of 2, you only need one of each in order to have a ratio of 1 to 1 or overall charge of 1. It's just CaCO3. Calcium carbonate turns out to be the compound that is made by most sea creatures to form structure. So like seashells, and the structure for coral is calcium carbonate. And whenever that's a rock on land, we just call it limestone. So that's what calcium carbonate is. Magnesium nitrate. So magnesium is in group 2 of the periodic table. It's just Mg2+. And then nitrate. And be careful that it's nitrate, not nitrite. Nitrate is right here. That's NO3 1 minus, or just minus. So because magnesium has a charge of 2 and nitrate has a charge of 1, you're going to need 2 nitrates to go with every 1 magnesium. Or you can do the cross-down method. So you got to have 2 nitrates for every 1 magnesium. Since we need 2 nitrates, and because nitrate is a polyatomic ion, it's a polyatomic anion, we got to put this thing in a parenthesis. So it goes Mg, and then it's NO3 with a 2 outside it. This way, we can tell that there are 2 of the nitrate anions. And it turns out here, when you count up the number of atoms in the element, there's 1 magnesium, there are a total of 2 nitrates, and there are a total of 6 oxygens. That's because this 2 kind of distributes in, much the same way as if you have a numerical thing, like if you have 2 times like 4 plus 3a, that's the same as 8 plus 6a. It's like you distribute the 2 by multiplying by the coefficients in each of the terms. It's the same kind of thing here, but sort of backward. 2 times 3 gives you 6 oxygens, and 2 times 1 gives you 1 or a 2 nitrogens. Aluminum sulfate. So on the periodic table, aluminum is Al3+, and then sulfate is right here. The formatting got a little messed up, but sulfate is SO4 2 minus. So the least common multiple of 3 and 2 is 6, or you can do the cross-down method. We're going to need 2 aluminums, and then we need 3 sulfates. But the sulfate, oops, that just got messed up. My pen just messed up a little bit, is SO4 3. So the charge for sulfate was 2, so we need 2 aluminums. The charge for aluminum is 3, so we need 3 sulfates. But that anion that's polyatomic goes inside a parenthesis. Lithium phosphate. So lithium is 1+, and the phosphate is PO4 3 minus. So because lithium has a charge of 1, phosphate has a charge of 3, you need 3 lithiums to go with every 1 phosphate, or the charge for the phosphate is the number of lithiums. So it's Li3 PO4. It's not necessary to put the PO4 in parentheses or put any numbers outside it. You just leave it as PO4. Okay, ammonium chloride. Now, this is an example of one case where you have a polyatomic cation, and ammonium is NH4 1+. And then chloride. Chloride is not a polyatomic anion. There's chlorate and chlorite. Where chloride comes from, and this "ide" is the key, is that it must be monatomic. And on the periodic table, you find chlorine as a halogen, and it has a charge of 1 minus. So we have ammonium with a charge of 1 plus and chloride with a charge of 1 minus. You only need one of each. The ratio is 1 to 1 for the charges. Even if you do the cross-down method, they each come out to just be 1. So it's NH4Cl. That's all you do. So a lot of these are fairly basic. The only thing you need to remember to do is if you need 2 or more of a polyatomic ion, then you got to put the polyatomic ion in parentheses and put the number after it. I'm going to leave you to do 7, 8, 9, and 10. And at the beginning of class tomorrow, we'll go over 7, 8, 9, and 10 as good practice. Okay, at the bottom of the page, it's that same paper. There are lists of compounds, and we want to name them. And it turns out it's not so hard to name them. And there are a couple little tricks you can do to try to figure out names. One thing I'll tell you is generally these polyatomic ions are usually anions. So oftentimes you can just look at the first element and see if that's a metal that appears on the periodic table. And it turns out that for all of these, the first element is the cation, and then there's a polyatomic anion. The only exception is down here, this NH4OH, this NH4, that's the ammonium cation. So here we've got this K, and then separately CH3CO2. So K is the element potassium. So the beginning of that name is just potassium. And then the CH3CO2, you can find that here. CH3CO2, it's a pretty big polyatomic anion. It's also sometimes written as CH3COO. There's different reasons to write it this way and that way, depending on if you're doing work in organic chemistry or thinking about it as a salt. But in either case, it's the acetate anion. It turns out that when this acetate anion bonds with a hydrogen anion, it makes hydrogen acetate, sort of. But when that's dissolved in water, we call that acetic acid, and that's what vinegar is. So vinegar is really a hydrogen with a C2H3O2. It's HC2H3O2. But this anion is acetate. You don't change the name. You just use the name just like it is. So that's it, potassium acetate. Here you have Mg. You'll find that on the periodic table. It's just magnesium. And then you're looking for PO4. That turns out to be phosphate. So here's the PO4. And you can also check the charges if you care. Magnesium on the periodic table has a charge of 2, and that's why there's a 2 here. And then the phosphate has a charge of 3 minus, and that's why there's 3 magnesiums. So it's just magnesium, phosphate. And here we have aluminum. And then there's a ClO3. That's not an I, it's an L. ClO3 is right here, chlorate. So the first element, just the element name for the metal, aluminum, and then ClO3, chlorate. 14, calcium is a metal. It's in group 2 on the periodic table. And then the SO4 is sulfate. It's right there. So we've got calcium. And then the SO4 is the sulfate. Uh, 15, on the periodic table, you'll find strontium. And then there's this HCO3. So sometimes when you look on this chart, oftentimes the name of the anion is related to the first element in the polyatomic anion. So here it starts with H, and you're like, oh, I don't know what to do. And you're looking through this list. It turns out the list isn't necessarily in alphabetical order of the first element, but it's in alphabetical order of the beginning of the name. So the H is related to hydrogen, and the HCO3 is right here. It's not the whole name that's listed. It's either hydrogen carbonate or bicarbonate. You don't write the whole thing. So there's actually two options. You can call it strontium hydrogen carbonate. But to be honest, that's usually referred to as strontium bicarbonate. NaNO3. So you got to find, well, sodium's on the periodic table. It's just sodium. And then the NO3 is nitrate. NO3 right up here. Sodium nitrate. So that's how the names of them go. These compounds look a little bit more complicated. You'll see that there's some things that are true about them. Pretty much all of these polyatomic anions have some oxygen in them. You might notice that's true. There's oxygens here, 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 here. Look at all these oxygens all over the place. So it's not uncommon to find oxygen present in polyatomic ions. Thiocyanate's an exception. Cyanide is an exception. Cyanide's a fun one. Hydrogen and cyanide makes hydrogen cyanide. You can also make sodium cyanide, and that's exactly what you think. It can be used as a poison. Any compound containing cyanide is usually incredibly poisonous. Another thing that you notice that's true about polyatomic anions is that if you need two or more of them, you'll find parentheses. So although this compound might look very complicated and very difficult to name, it's actually quite simple because the HCO3 itself is a polyatomic anion with a certain name. And you don't have to memorize any of these. You get to use the chart anytime you need. What's important is to be able to utilize the chart to be able to come up with names in the formulas. All right, so hopefully that makes sense. Those are all correct. I record every class anyway, so you can always look on the YouTube channel, or if you check on the plan for the week, right beside where it has the date on the website, I'll show you what I mean. So here, like where it says plan for the week 12/7 to 12/11, then like right beside the class, it'll say Zoom recording. Oh, wait. Oh yeah, today is Wednesday. Oh, that's good. This week's been dragging. I felt like it was Tuesday. So this is the Monday class yesterday, and today it'll be here. I mean, as soon as this class is over and I can save the recording, upload it to YouTube, put the link on here, it'll be there. But I also put, this is the link to the notes we went over, link to the polyatomic ion chart, and these are the practice we just did. So what you should do, with the remaining few minutes here, if you haven't done it or you're working on it right now, finish like the last few that I didn't do as examples on the practice. And then tomorrow at the beginning of the class, we'll go over that, and I'll show you how to name and write formulas for ionic compounds that contain transition metals, which are metals in the D block of the periodic table. Yeah, so do like 7 through 10 and the 17 to 20 is practice. If you have questions, you can put them in the chat, or you can turn your mic on and ask them. If you're confused about something or you think something was incorrect, just let me know. Otherwise, that's it for today, and we'll catch you tomorrow, same time, same place, 8:30.